Good morning. We're just going to give everybody a few minutes to log in here, but we're going to start you off with a poll and see who knows what the WASP stands for. Well, so far, 86% got the correct acronym.
Outstanding. I'm not even sure we need to do the demo now.
Yeah,
Exactly.
pack it in.
Got almost everybody has answered the question here. So yes, sir. 88% is wireline applied stimulation pulsing. That's good to go. I'm going to start us off with just a few housekeeping rules. Today's event is being recorded. A link will be shared with you after the webinar is complete via email. We welcome you to revisit the content yourself and share it with your colleagues. This demo and its contents will also be available via the BlueSpark YouTube channel. All attendees are on listen-only mode, so you'll be muted throughout this demo. If you have a question for our presenters at any time, please enter it in the Q&A box. Todd Parker, our CEO, will be working with Rob Harries, Global Operations Director, to answer them as we go. Some questions may be held for the Q&A portion after the demo is complete. Note that due to increasing users on many online platforms, you may experience intermittent availability on HD video during the live event. During the presentation, we'll have several polling questions. We just did our warm-up one there. Thank you for taking the time out of your busy schedules to join us. And now we'll get started with what brought you all here today.
Thanks, Steph. I'll just say a couple words. It's Todd here. Welcome everyone to our first virtual demonstration. I think as everyone is wrestling with the impact of COVID-19 around the world, we're all learning how to both work remotely and also connect with people remotely. Typically in the past, we have invited customers, friends, family, and anybody else that was interested in high pulse power to our facility to look at the tool, to see our technology in action, and to discuss what it does, how it does it, and more importantly, how we manage to make it work safely, effectively, and efficiently for our customers around the world. I would say every time we have customers come and see the technology, we get some excellent questions, number one. And number two, we get some great ideas and conversation going about what it can and can't be used for. And ultimately, we get some believers that this is actually a technology for the future. Because of the pandemic, of course, the ability to bring people to our facility is a little bit limited. And like everyone else, I think we saw that as a shortcoming in terms of how we do business. I think the reality is it's actually really opened our eyes in terms of how many people we can now virtually invite to our shop and show them how things work. So at the shop, we have Rob Harries, who is our operations director. He's responsible for managing the delivery of the services globally to well sites, offshore platforms, land sites, and what have you. He is going to take us through a little bit of the history of our testing and development, the building of the tool, show us the components of the tool, and go through some safety and some logistical things to keep in mind. And ultimately, he's going to pulse the tool for us in a simple target and just give a basic demonstration of what high pulse power can do in your well site. One thing I want to always note to people is that pulse power is the effective use of very small amounts of energy to create high power events. If we were running this entire demonstration from your cell phone, by the end of Rob's demonstration, you would still have more than half of your cell phone battery life left. That's how low of energy we're talking. But in terms of the power output, what you're going to see is almost a gigawatt in power being produced through the life of the demo. Steph, how about we do one more poll question, and then we will turn it over to Rob to get started. So during the pandemic, I think we've all learned to adapt to different work environments. Working from home has proved challenging for myself and for the people here at BlueSpark. But like a team of champions, we have overcome and adapted and made some new work spots, our new work spots. And so just a quick poll, what have you found has been your effective working away from the office location?
We've got almost all of our votes in here.
Perfect. And once that wraps up, Steph, and show us the results, we will take it to Rob.
Okay.
Oh.
I wish I had a home office. My living room is.
Yes, well, I'm going to have a hard time going back away from my couch, to be honest with you. It might have to be an office furniture improvement. Okay, Rob, over to you at the Blue Spark Batcave to kick us off.
Excellent. Thanks, Steph and Todd. Everyone, welcome to the demonstration. Steph
actually,
mentioned.
Rob, I'm going to pause you for 2 seconds.
Sure.
We've had some new people join. I want to point out to everyone that there is a Q&A box that you can open up. And as Rob is presenting, if any questions come to mind, please type your questions into that box, and either I will call out the question. I will either call out the question and either Rob and I will answer, or maybe the more complicated ones that we will leave to the end. We have a question right off the bat, Rob. And so it's in relation to the jersey you're wearing. So I think it's kind of a two-parter question. First and foremost, why are you wearing that funny looking jersey? And then secondly, why are the sleeves so short?
So everyone at Blue Spark that joins gets a hockey jersey with their employee number on it. It's a bit of a Canadian tradition that we are hockey fans. The sleeves are short because the CEO orders the short sleeve shirts or for T-Rexes. So that's what I'm stuck with.
Thanks, Rob. Why don't we go ahead and start it off?
You bet, you bet. So again, thanks, Steph and Todd, for the introduction. Everyone, welcome to the demonstration. As Todd mentioned, there's a Q&A you got to type into. We appreciate any and all feedback, whether it's from a demo point of view, ideas point of view. Don't be shy. So I'm going to take you through a bit of history on Blue Spark, a bit about the tool itself, some of the applications we've tested, and then as Todd mentioned, we'll do a safety discussion around why we think this is a safe alternative, and then lastly, you get to see high pulse power in action. We're not in a real life, a real well example here, but really does give you an indication of what high pulse power can do, affecting some change. So Blue Spark Energy started in 2011, a small startup company in Calgary, Canada. The idea was to take this unique technology and try and inspire some energetic change amongst the applications that we're targeting. We first focused on producing wells. In 2011, the price of oil was quite high, so it made sense to go after a couple extra barrels. As 2014-15 rolled around, that changed a bit, and clients then asked us to focus a bit on injection wells. Same principle, high pulse power, liberate fines, bust up scale, delaminate waxes and asphalt beams. But that was the focus, production and injection. It wasn't until 2016 clients came to us and said, can you clean a subsurface safety valve? We said, well, but what's the problem with the valve? And they told us it was scale or fines. And we said, sure. And really from then we've had a big boom in application for wellbore integrity, whether it's subsurface safety valves, cleaning up gas lift systems, cleaning areas for plug sets or straddle packers. And that's really where most of our business is today. When we first started in producing intervals, the clients said, how do you compare to existing technology? And for us, it was kind of difficult. No one else uses high pulse power. So we thought, well, let's take a perforating charge and how they test that. And then perforating charges are tested in what's called an API 19B test block. It's a cement block where they measure the entrance hole and the penetration length. So we built an API 19B type block. We put the WASP tool in the middle. And so after a few pulses, we busted the block into a bunch of pieces. Now again, we're not getting entrance hole, we're not getting penetration length, but we're showing how high pulse power can have an impact on these screwed up components. The next example that was more applicable really is a 7-inch piece of pipe with perforations. And so we gave it kind of a zero perm environment. We cemented up the perforations, stuck our tool in the middle, and again, pulse. So these are the first two starting points for us in terms of how we compared, and then clients then filled the gaps for us. They sent us premium screens, slotted liners, some SAGD applications, pump housings, sliding sleeves, frac ports. We've tested a ton of material and are happy to test more. But in each instance, where there's a component that we can be in front of, where the WASP can be in front of, we have a great impact on breaking up scales and liberating fines. With the samples client sent us, with our wellbore or with our well site visits, we were able to collect the sample set as well from many scales. Today we have a book of about 40 scales we've treated, and to date we can't find a scale that we can't beat. So it's, so far high pulse power is a great application for scale in terms of improving flow, injection, or helping restore wellbore integrity. So Todd mentioned a bit about high pulse power. For those that don't know what it is, in a nutshell, it's the rapid release of energy in a very short period of time. We use electrical energy. Our governing equation is power equals energy over time. So the energy piece is limited. We use wireline industry standard cables today. They've got a voltage and a current rating, and so there's a set amount of energy we can deliver down the cable. So we don't play with the energy piece. What we play with is the time piece, how we charge the tool and release that energy. We're able to turn 1,000 joules of energy. So 1,000 joules is a couple tablespoons of orange juice, a couple of sips of Coke, or a bite of a chocolate bar. 1,000 joules gets turned into 200 megawatts. That's a single pulse. Now, 200 megawatts, it's essentially a generating station for a small town, a small city. They would give that power 24/7 to obviously power the lights in that city. We give it for 4 to 5 microseconds, very short burst of energy. Any questions so far on that, Todd?
Yeah, Rob, we have a question. Since we use such a small amount of energy per pulse, what are the possibilities of running this either by battery or by slickline?
So one of the issues we have with battery, the battery length itself would need to be several tens or hundreds of meters long in order for us to perform a treatment over a select interval. So that's the limiting factor right now on slickline or on memory.
Okay, thanks.
Excellent. So I'll take you down and talk a bit about what the operation looks like next. For us, for those that are knowledgeable with the industry, we are similar to a case fill operation. There's a rig up process where we connect our individual sections up at the wellhead. We run into the well, and we then correlate to depth and then stimulate the interval we're asked to stimulate. Once that's done, we pull out of the well and then rig down. So an operation for us can take anywhere from, I guess, 10 to 14 hours, depending on rig up, rig down, and depth of the well. When we go to the well site, we have a standard kit we bring with a couple exceptions. One of the exceptions we bring is called a safety kit. Now I'll talk a bit more on safety when I get to the tool. Safety kit allows us to detect energy, high energy, discharge that energy, and keep our guys protected with PPE, whether it's high voltage gloves or what have you. The second set we send to the well site is a full test kit, and the test kit allows us to measure the electrical chain from the top of the tool to the bottom, ensuring we have the tools in a functioning order. So it's more of our QA/QC piece that we can do at the well site. When we're at the well site, we need to connect up to the wire line that's there. We bring our own power supply. We bring our own supervisor typically. We do have third parties that run our service depending on the environment. But we have our own power supply, a laptop. We essentially borrow the cable for a short period of time, send our low voltage, low current down to our tool, and then the tool does the rest. I'll take you to the tool now. So this is the actual tool we'd use in the well site. We've got a bit of a change on the bottom with a jumper cable just so you don't have to suspend the tool from the roof. The tool itself, all our tools have an industry standard GO connection on the top. It's 1/11/16. It allows us to connect to almost anyone's wire line. The electrical requirements are 500 volts, 1.5 amps roughly, and that allows us to use 99.9% of the existing cables out there. So it's very adaptable to what's in the industry. We have two tools in existence today. We have the 2.75-inch version, and we have our skinny version, which is 2 1/8. So very similar tools. Both tools are rated to 10,000 PSI. The skinny tool is rated to 120 C. The fat tool is rated to 130 degrees C. The length of the tool varies between 11.7 meters and 13.1 meters. And the top of the tool is really the smart part of the tool. This is the tool that takes that low voltage, low current and does all the amplification. Now, this is the part that generates the risk. So this generates the high voltage, high current. As soon as we turn power off, obviously there's no high voltage, high current. The risk piece lies here in the capacitor section that allows us to store the energy. Stored energy release is the issue that we face if something were to go wrong. So how do we combat that? From the hierarchy of safety controls, there's administration, there's engineering, there's substitution. For us, we start at the engineering level. So we have two devices in here that will kill the energy should we charge up the tool and not release what we're supposed to. The active safety device is in the top of the tool. It requires a certain voltage to open the relay to the tool string. When it's closed, it closes to a resistor. And so this tool, we apply power at surface, we charge up the tool. The second we stop applying power, it closes to a resistor and dumps any energy that's located in the tool. That's our defense number one. Defense number two is a passive safety device. This tool has 6 resistors in parallel. The current takes the path of least resistance. It avoids the resistors and comes to the capacitors and charges those up. The second we stop applying power, if this is energized, the ASD kicks in. If the ASD fails, the resistors take roughly 15 minutes to dissipate any leftover energy. So in our procedures, we have a step where we wait 30 minutes post power down just to ensure this and this have had a chance to de-energize the tool, making sure the operation is safe. On the safety front, this tool has no chemicals, it has no explosives, it has no radiation. It's essentially dumb steel with a couple batteries. As long as we have a way to control the energy in the batteries, which I've just explained, there's absolutely no risk to the well site.
Rob, can I interrupt with a few questions?
For sure.
So we've had a question regarding clarity around the battery comment. So the fact that a cell phone battery is so small, why are you suggesting that a battery to run the tool would have to be tens of feet long?
So one of the key aspects of our batteries is they not only have to store the energy, but they have to have the science to release it incredibly rapidly. That's what creates that high power. And so the design of the batteries are such that this is the shape, this is the length we take today in a downhole configuration. And for us to try and power this with a battery would take, we've done calculations of a 100-meter battery section above. So today it's unfeasible with current technology. That's not to say down the road there's some R&D projects that we can't put into place to try and do it on cyclone.
That's a great question, Rob. So I think it's not necessarily in the essence of how much energy that's being used. It's the fact that we need to release that energy in microseconds. So the cell phone battery that you're referring to, that's designed to release small amounts of energy over a long period of time. Our tool is the exact opposite. It releases a tremendous amount of energy, really only 1,000 joules, but it creates that power effect because all of that energy drains out within microseconds. Similarly, your battery is used to charging, within an hour's time frame. We need to be able to charge our battery within 3 to 4 second time cycle. So in 3 to 4 seconds, we need the battery to be charged to full capacity, and then at the same time be able to release that capacity in microseconds. And in terms of battery technologies, that actually is a level of complexity that really limits both the footprint and the availability of the materials that we can work with. I've got a couple other questions maybe that we could get to. So yes, we had a question, are the batteries that you're referring to, Rob, actually capacitors? And that is correct. The capacitors in the tool, we use interchangeably as batteries or capacitor in terms of terminology, but they are in effect capacitors that we've developed to handle the electrical capabilities that we require for the tool to function. A second question that we've had, Rob, just in terms of the number of pulses, and I'm sure we'll get to it, so you can answer this now or answer it later, in terms of number of pulses that we deliver, and then what effectively does that mean in terms of the amount of meters that we could treat in a single run in the well?
I will get to that in about 2 minutes, and I'll show a little bit of example on why there's the issue on a limit on the number of pulses.
Okay, and one last question we'll take now is around the temperature limitation. So you said 120 degrees C for the 2 1/8 inch version of the tool, 130 degrees Celsius for the 2 3/4 inch version of the tool. Can you just give a brief summary of what limits or what creates that limitation of temperature for us? Is there a specific component?
There's 2 components that really limit that. So the capacitor technology is affected by high temperature, and also the internal electrical system on the charge unit, the upper asset. We generate about 40 degrees C of heat internally in the tool, as we're feeding in that current feed. So we generate a ton of internal heat, and then, as I say, the batteries themselves can't withstand the temperature rating that we currently are listed at.
Perfect. Thank you very much.
Thank you. So we'll move down. I'll get to the pulse point here, or the number of pulses, very shortly. So the capacitor section makes up the majority of the length of our tool. In the 275 version, it's about 7.5 meters long. They're all in sections less than 2.5 meters. The business end of the tool is here. So for us, storing energy, not so exciting. It's the release point that's super exciting for us, and where we really enjoy the opportunity to bring clients and have them feel the high pulse power in their feet when they're standing by the demo. You won't be able to feel it on your couch, but hopefully it'll give you an indication of the impact of what high pulse power can do. So the capacitor section stores the energy. Once it releases a certain voltage, there's a tool called a power amplifier that's designed to release that. So what happens is we get the 30,000 volts, we jump across an anode cathode system here, and we get to the business end of the tool, which is right here. So this is our closed electrode section. This is the part where the pulse happens. The pulse happens right here. We run a membrane system with our tool, and the reason we do that is so we can keep a known dielectric fluid between this anode cathode area. Brine, heavy oil, all these would change the properties. This allows us to keep a consistent environment for us to pulse in. When the pulse happens, we have all the dump of high voltage at the top. It comes down this tool here. There's insulation. It hits the anode and jumps across to the cathode. When it jumps, it creates a plasma arc, which initially makes a shock wave. That plasma superheats the water, creates gas or volumetric expansion. That makes a hydraulic wave. So this tool has to be in fluid for it to work, has to be coupled to the problem. So as long as we have fluid between us and the scale, we'll have no problem transmitting the shock wave and hydraulic wave to bust up that scale or remove those fines. This is the wear and tear section as well. So this membrane, this insulator, this anode and cathode have significant wear and tear over the process. And so what happens is we erode the anode, we deteriorate the insulation, we deteriorate the membrane. Today we can get 6,000 pulses on this. What 6,000 pulses means is we can treat up to 60 meters or 200 feet in one run. Depends on the environment, depends on the scale type, but that's currently what we can do. 6,000 pulses up to 60 meters treatment. If we have a longer interval than 60 meters, all we have to do is pull out of the hole, unscrew this connection here on the tool, install a new electrode section, run back in the well. It can be about 20 minutes to swap out the electrode section. Okay, any questions on that, Todd?
Yeah, so I mean, great showing us the limitations around the anode cathode design. A simple question is why don't we run more than one anode cathode in the electrode section, so that as one burns out, we could just quickly switch to another one without having to come out of the well?
So very interesting question. We actually have some R&D down that path today where we're looking at a multi-electrode system to allow us to last much longer downhole. Currently in the works, so hopefully in the next few months we'll have something confirmed, and we can hopefully treat longer intervals for clients and make it even more economical for them.
I think one more thing to point out with the anode cathode, even though we talk about that 1,000 joules of energy, because it's released in microseconds, we're talking a 200 megawatt power event. So practically that is in the tens of thousands of volts and tens of thousands of amps that is traveling between that anode and cathode. So it's not as simple as, I guess what I'm saying is that it actually withstands a tremendous electrical event, which is what causes the degradation, but also creates some limitations around the space that we have to provide around that electrode for it to function properly. A question around being able to perhaps reduce the length of the tool. Your capacitor sections look kind of modular. Are you able to add or subtract capacitor sections to make the tool longer or shorter? And is there any trade-offs to doing that?
Yes, we can. So as we add and remove capacitor sections, we change the energy input. And so let's say we remove one capacitor, which takes our energy now from 1,000 joules to, let's say, 666 joules. That's the only difference. Now there is, based on our application testing, based on our understanding of scales, we have run our tool in a reduced configuration. to allow for us to treat, let's say calcium carbonate, for example, which we know is a much weaker scale type. So there are ways we can tweak the length of the tool. We do have a prototype tool essentially that's got a much better capacitor design, which we're still working on, which can allow us to actually take away a capacitor section and have the similar output to what we have today with a 2.5 meter shorter tool string. It's currently in field test now.
Great, thanks. And is there any limitations in terms of running this with other tools or other sensors, such as calipers, other things like that?
Good question. I forgot to mention that at the top. So our tool is a bottom-only tool, but above our tool, we can run, we run on tractor. We have a job loading out June 1st with the tractor. We can run PL tools. We can run caliper, release devices. There's no issue running tools above. The issue is running tools below.
Okay, thanks.
Okay, we're going to get to the demo section here shortly. What we have to show you today is a 5.5-inch piece of casing. We've given it a bit of a fake scenario where we've cemented off the perforations. Again, not real world, but it allows you to see the impact of high pulse power. A couple of things to note when we do this demonstration. Number one, the steel is not affected. 1,000 joules of energy is insufficient to damage the steel. Plus the steel acts as almost a perfect reflector. It reflects back 94% of the energy. So if there's nothing brittle between us and the tool for us to remove or break up, it just, the wave reflects back a couple times, the energy dissipates and goes away. That means our treatment length is less than 1 meter in length we treat at our pulse point. And so if you've got a water zone you want to stay away from, a sensitive completion component, whether it's a gauge you want to stay away from, we have no problem being selective on where we put the tool to pulse. Another key feature, we have no path of least resistance. The tool pulses omnidirectionally. The pulse happens so fast, it keeps creating surface area, or in this case, keeps opening up perforations for flow. Unlike an acid job or a skin frac, the second you have a path of least resistance, all of your fluid gets essentially directed to that one pathway. We don't have that issue. We're going to get to pulsing here. Ryan's going to go and power up the tool. I'm going to change the camera angle and zoom in. This exact target's in here. We're going to show you this. As Todd mentioned, this entire demonstration will be done with less energy than you contain in your cell phone. We're going to pulse roughly 15 times, and then we'll pull the target out and show you.
And Rob, just to clarify, that's a 5.5-inch piece of pipe with perforations in it that you have wrapped with cement, and there's some chicken wire in there as that mix as well to try and hold that cement on even better. Is that correct?
Correct. Yeah, the chicken wire essentially holds the cement in place. Otherwise, we just pulse and all the cement would fall off. So it's not really good at demonstration point of view. I will clarify on this. Your cement behind steel, so where we clean off plug sets or where we're treating SSSVs, your cement behind steel is unaffected. That steel reflects 94% of the energy. Okay, bear with me. I'm not a videographer, but I'm going to position the zoom on here. We can see that okay?
It's like we're right there, Rob.
Awesome, awesome. Let me get my headphones on. Bear with me, I won't hear you guys for the next bit of pulsing.
Todd, I think this would be a good time to do our next poll. Oh, no, sorry.
Well, as you can see, as we pulse approximately every 4 to 5 seconds, we're releasing that, let's say 200 megawatts, which is effectively a shock wave due to that plasma that we're creating between the anode cathode. And the superheating of the liquid inside that rubber membrane that Rob was showing creates a pressure wave. And that is the combined effect, expands radially outwards from the electrode. And as Rob said, pushes or disaggregates the material that's in front of it. The pipe itself isn't affected. As Rob said, we do not have enough energy to move, shape, or damage that piece of pipe. But we do have enough power to push or break the cement in front of those perforations. That's the material that we're disaggregating. If that were scale of any type, it would do equally an equally effective job. And what you'll note as we pulsed, even though 1 or 2 holes opened on the first 1 or 2 pulses, As we continue to pulse, we just continue to open up holes around the target. As Rob said, there's no point of diversion. If that had been a chemical treatment, as soon as we had opened 1 or 2 holes, the chemical would start leaving that area out through those holes, and you would have a less effective chemical treatment. By continuing to pulse, the pulses happen so quickly, they don't realize that holes are open, and they'll just continue disaggregating material that it can leak.
Thanks, Ryan. All right, here's the finished result. Steel's intact. Cement where the holes are located has been removed.
Boy, if we could get that closer to the camera, that would be so good.
Sorry, Todd.
Oh, see, I knew that was going to be so good.
You can even see here, we've got chicken wire on that perforation, not damaged. It's, if you ever thought your cell phone could bust open cement, you might think about your cell phone differently, but this is a prime example of how we use high pulse power to affect the change downhole.
Excellent. Rob, can you show the chicken wire? Yeah, so as you can see, just to go back on that, how much energy do we have and can it damage steel? That chicken wire is not very strong, and you'll see that we have no effect on that. It's the material, the ability to break up or disaggregate the cement, or in your case, in your weld scales or inorganic materials, is what really makes this tool so powerful. The fact that it is non-contact, non-chemical, low energy, and ultimately non-damaging way of just peeling material off of what it's adhered to is what makes it so powerful. A couple questions coming through, Rob. First and foremost, when you showed the electrode and we were pulsing within that piece of casing, we couldn't see it, but do we see massive elastomer expansion when we pulse the tool, number one? And number two, is that cause for any kind of concerns around pulling out of the well after a treatment?
Good question. We do have an expansion of the membrane for sure. We use that type of membrane to allow that expansion to happen that transmits the wave. We are just under 600 jobs, probably close to 1,500 runs in the well. We've never had the membrane cause us an issue to get out of the well, but we have had some gasified due to CO2, H2S when they come to surface, but no, we've yet to have an issue.
If we had been pulsing in that tank without that casing, would you be able to see the elastomer expanding yourself?
No. So one of the challenges we faced early on was trying to measure the effect of the pulse. We used cameras, high-speed cameras. We now have settled in. Our R&D, our projects manager, Chuck, has found a great way to measure with a gauge. You can't see it with the naked eye. You need a high-speed camera that, I guess, a millionth of a second, it'll capture the pulse of the membrane. We do a video of that online we can share with you as well.
Okay. So, I mean, it looked like the tank was moving around a little bit. Looks like quite a powerful event. When you're running this on a wireline cable, is that something like a perforating gun you would feel back at the truck or at the winch?
No, the only reason that you see the tank jumping is just that 1,000 joules causes a bit of a momentum. We've got a horizontal tank that we run. It'll ripple the surface of the water. It's very localized, so you'll feel nothing at surface. Where we have pulse close to surface, we've heard the noise. Again, that was in a no fluid environment where we ran a fluid hold-up tool. It's slightly different, but no, it's very localized.
So that chicken wire actually, if you wrap that more densely, would start to look like a wire wrap screen. Would this be a good tool for cleaning wire wrap screens?
Absolutely. We have some samples of wire wrap screens we've tested. We've got some well examples where we've treated wire wrap screens for production or injection enhancement. So absolutely.
You mentioned that we have to be in fluidic contact with whatever material it is that we are trying to clean. Do we have any means of making sure that we have fluidic contact, or is there a way of running this in wells where we're going to be above the fluid level, or maybe even a gas well?
Two-part question. Our tool has no way to tell it's in fluid. That's one design flaw we're working on. I wouldn't say design flaw. That's one limitation of having a bottom-only tool that's got 1.5 amps running through it. We do have what's called a fluid hold-up tool. So on the bottom of our CER, the bottommost tool, we have a GO connection. And we've designed a mandrel to go on the bottom of this that has rubber discs, and the discs can be any OD. And the idea is that these rubber discs will suspend sufficient fluid so that the pulse point is in fluid at all times.
What about just running a larger electrode that would be in physical contact with the wellbore itself?
So the size of the electrode doesn't matter. We could make this to 10 inches in OD. This is not going to change. The point source is not going to change where the pulse point happens.
Yeah. So I think the question, Rob, is, you know, how if there is no fluid, how can we make sure that shock wave transmits to the debris? And so, I think there's two trains of thoughts. I think what was suggested in the question was maybe you just make the membrane expand out so that it touches the material. We've addressed that differently. As Rob said, we have the fluid holdup tool. We just create a portable fluid column that travels with the tool, if you can imagine that. And we just allow the shock waves to travel through that portable fluid column that we've made. A couple questions around compatibility in terms of tools or other things. So you mentioned we'd run it on wireline tractor. Have we ever run it on coiled tubing?
Yes, we have. We run it on e-coil several times here in North America. And we had a job in the North Sea as well on e-coil.
Yeah, so it has to be on e-coil. And then a question around depth control. How do you know you're positioning it properly in the wellbore?
Good question. So there's a couple ways we can determine or confirm depth control. One is we can flag the line with a CCL run. Typically, we run a CCL with our tool string. So any wireline provider of your choice is capable to run our tool. They have the experts on depth control. They have the CCL. So we would just let them correlate us, and then we go ahead and pulse away.
Perfect. Well, thank you very much, Rob. I'm sensitive that we've run 5 minutes over time, so we could, no, you've done a great job. Thank you very much. And I thank you to everyone that has attended. I hope we have answered your questions. If you do have follow-up questions, please reach out. Steph, I'm not sure if you have our contact details that you can show. Failing that, www.bluesparkenergy.com would be a great place to come and look for contact information. And additionally, we have about 40 case studies now posted on the WASP success. You can sort those case studies by application, by region, and the problem area that we were trying to address. So please go to www.bluesparkenergy.com and either reach out to us or satisfy your curiosity around what we've done with this tool in the past. One last question, and then we'll wrap up. Can you pulse across a restriction, and would that damage the membrane, preventing you from completing the operation?
We have pulsed across restrictions, so there's nipple restrictions in the well site we've treated. No, so a manufactured completion, a manufactured restriction like a nipple will not damage the membrane. If there's a tear in the casing or tubing, that's possible, but no, a standard restriction in a well site won't pose a problem for us. The membrane is quite flexible. It's I can bend it, but it's it'll conform to the restriction itself and still allow that hydraulic wave to pass through.
Okay, well, great. Thank you very much. We appreciate the virtual shop demo, and again, for all the attendees that took some time to come and visit us virtually. Thank you for the time. Again, any further questions, reach out to the webpage or through the webpage. Look at some of the stuff we've done. There's some videos there. You'll get a link to this presentation as a follow-up, and that would be an avenue to reach back out to us if you have further questions or would like to get some more information. But otherwise, thank you very much. I appreciate everyone attending, and thank you to Rob and Ryan at the Bat Cave putting all this together for us. And Steph, thank you for being in the background and keeping us on track. So thank you very much. I think we can wrap this up.
Thank you.
Thank you.